All right, so welcome to Supercognition. Today we're going to take a look at a fun paper from Jeff Clune on AI GAs, so generating algorithms that generate AI, and looking at what that means in the context of generating both the agents and the environment. We'll have some fun questions for Aubrey about his 3D world synth. Aubrey, tell us a little bit about what you're doing with your synth platform.
Absolutely. I've actually spent a large portion of my career trying to find ways to catalyze human intelligence. So, like learning in young children, enabling creativity. We all have this creative voice inside of us that loves expressing itself. And I've found that in conventional creative mediums, there's often a pretty steep learning curve to use the tools and develop what I call the vocabulary of creative expression. Whether you take a class to learn to oil paint or any other example we could name, when computers enter that equation and we can begin to develop amplified feedback loops where the human creativity and intuition can be enabled, facilitated, and multiplied by the computer tools. A great example might be some kind of Photoshop plugin that turns a very primitive style painting into a beautiful looking watercolor. What I've been doing in my background with virtual worlds is a project called Synth, SYN3H, and the vision of this project was to take the idea of free-form creative expression in terms of world building, a similar experience in terms of your actual mental engagement to perhaps building something cool out of Legos inside of a digital environment. And of course, one of the beauties of that is you never run out of Legos. Another one is that it's inherently collaborative. And to me, an even cooler takeaway as part of that experiment I started running over a decade ago now is that when you're doing this on the computer, you, as perhaps the 9-year-old, perhaps the 13-year-old kid, see your personal computer less as a consumptive entertainment device and more as an engine, essentially the most complicated machine, the most complicated electronic system in the known universe, sitting there at your beck and call, waiting for you to tell it what to do. I love to think of computers as amplifiers and enablers for human expression and flourishing. And so my interest in virtual worlds was in building free software that could encourage kids to explore their potential as engineers, as perhaps programmers, mathematicians, and to do that in a super artistic, intuitive sort of way. One of the big things I hit was this idea, specifically, this idea that if I, as a human user, have very simple inputs to the system, and the system itself can begin to extrapolate the extra detail of, oh, you're using stone voxels and you're building something that looks like a bridge, perhaps it can build the entire intricately detailed three-dimensional structure of the bridge with the underlying keystones and arches and cobblestone paving and everything else, where the more believable the world feels to us humans, the more creative we feel like we are, and the more creative we feel like we are, the more creative we actually become. But circling back to this paper, this idea of a learner in a simulated world in a virtuous feedback loop with this environment holds so many possibilities.
Yeah, and Jeff Clune's paper proposes this idea of evolving the environment. And so, since you've been working on this synth platform, I thought it would be cool to kind of explore this paper and chat about these concepts. I'm a big, huge fan of Jeff Clune's work. He's kind of a maverick in the AI space, working in areas that are not explored by many researchers, which I really appreciate because I think we need more diversity in the AI research. In particular, here he's proposing in this paper, which has been out for a while, but this paper he's proposing an approach to AI that's completely end-to-end learned rather than building thousands of narrow components and then trying to combine them in some ensemble or something. He's proposing that we evolve agents along with an environment. And since you have built a full 3D world environment, I thought, you would really have some insights and some intuitions for, what that would look like. So, as I mentioned, this work really hits on a lot of interesting ideas, which is, about the deceptiveness of reward functions and how exploration and all of Jeff's papers are kind of in a similar vein about the need for more exploration and more curiosity and open-endedness in these algorithms. And I think evolving the environment along with the agents does potentially introduce a full open-ended environment. Like that's the open-ended reality in which we currently live is an environment that is evolving alongside us as a species. So, we're watching the Earth, for example, go through temperature changes right now, and that evolution of the environment along with the agents, I think, is a contributing factor to the endless forms, the biodiversity that we see, on our planet, because you get not a single, you don't get a single model of the world instead, or a single type of agent. Instead, you get a distribution of agents, which is more of a population search method, which I find to be fascinating as an approach to overcoming these deceptive loss functions, these loss function traps.
There's a section of this paper, specifically it's page 12 in Jeff's publication on the archive. I'd love to actually read here because he describes this topic so beautifully. And here I'm quoting Jeff. One essential component of QD algorithms that fuels their success is goal switching. The idea that within a niche, a particular vector is optimized to perform well, but if at any point it turns out that a perturbed version of that parameter vector belongs to another niche and is better than its current champion, that perturbed parameter vector becomes the elite in the other niche. That enables one style of solutions in a niche, which may be stuck on a local optima, to be disrupted by another type of solution that was discovered via optimization on a different niche. This captures a dynamic similar to scientific and technological innovation, e.g., how microwaves invaded the kitchen niche despite their underlying technology being developed for radar, a very different purpose. It also captures the dynamic of natural evolution, where a species optimized for one niche can invade a new niche if it is superior. Research has shown that such goal switching significantly improves the performance of QD algorithms. For example, we showed how it can enable the creation and combination of different skills to produce multimodal robots capable of jumping, crouching, running, and turning. QD algorithms can be used in many types of problem domains, such as solving different types of mathematical, writing, or musical challenges. For example, in our work on innovation engines, we showed that the same ideas underlying QD algorithms could be used to generate different types of high-quality, recognizable images. Goal switching proved essential to avoid local optima and was a catalyst for innovation. We also observed in that work another hallmark of biological complexity explosions: adaptive radiation. Innovations in one niche rapidly spread to many other niches, allowing key innovations to spread and become the foundation on which additional innovations specific to different niches are built. This phenomenon is reminiscent of the Cambrian explosion, wherein the innovation of the four-legged body plan led to a rapid radiation of that motif into a large number of different niches to ultimately produce all of the diverse four-legged creatures on Earth.
Yeah, beautiful. I love the quality diversity algorithm. I love the map elites and the approach of finding populations that are each elite in their own niche environment. And I think this is just going to be fun to watch. I feel like this is one of the essential components to achieving AGI will be a population-based search where we allow for goal switching and allow for the perturbed version of elites in one category to end up becoming the elite in another category. And I think his work in this field, Jeff's work in this field, has already shown that it does look like somewhat of an evolutionary. Um, it's very analogous to the way that biological evolution produced these endless forms most beautiful. It's really cool, and I think what he showed is that there's a very circuitous path. Oftentimes, if you trace the lineage of any best elite algorithm, it didn't just stay in its particular part of the environment, but it was elite in various other parts of the environment, which I guess shows that um, it shows the serendipity that sometimes emerges from exploration, right? So, for example, the radar example, learning radar, learning about radar, right, allowed us to improve on kitchen cooking, and there's just endless examples of that, right? I mean, if you're wanting to do math faster, it turns out that working on vacuum tubes is one of the steps involved in, arriving at integrated circuits. And so, I think the whole history of science and technology is this very circuitous path of exploring. And I think that's why science is valuable, and we should be exploring the frontiers of science in all domains, is because we don't know where the next breakthroughs will come from. We don't know which fields those will be on. And so science is the process of trying to explore those boundaries. And I think that is awesome. And I think that's probably why I like Jeff Clune's work so much, and just because it really resonates with like my mind and the way that I try to explore all of these. I always try to look at ideas and see where's the circuitous path to a new breakthrough. So yeah.
This paper specifically describes three categorical pillars in terms of architectures, algorithms, and learning environments to facilitate the generation of general intelligences. And there were a few things, Zach, that you and I thought would be really interesting to explore more in this conversation together. One that I had written down here, writable memory and neural Turing machines.
Yeah, I think that this gets into some of the, I think Graves was the one that did the DNC, the differentiable neural computer. And I think it's a very interesting way that we can augment neural networks is by giving them read and write heads to discrete memory banks. And I think, yeah, I think that he refers to this as one of the, in the paper, he's referring to this as one of the pieces to intelligence that right now is being built out as like a separate individual module or component, one of many. And this is more in line with like the manual path to AI. But potentially discrete memory would be something that would be learned as a mechanism by an AI GA as well. So potentially a generative algorithm would eventually learn to create discrete memory banks. As, for example, through evolution, we've seen that humans have some form of discrete memory, although it's arguably not discrete. When you look at it more closely, it appears to be it's stored over representations, so it suffers from loss, and it's not optimal for discrete memory. Let's put it that way. From a Shannon information theoretical perspective, discrete memory could be much more optimal if it were stored in its actual form, rather than being learned in the parameters of the network. So, but yeah, that's one of the components that he's referring to here on page 3 that I've been fascinated by is I think the ability to augment neural networks with these discrete memory banks. I think it's worth exploring further.
Let's talk a bit more about learning as such in terms of the human memory system optimizing for the recall of inputs, emotional states, and outputs at the expense of much higher fidelity, sensory, tactile, etc. information that we didn't deem to be relevant through the focus of our attention. Jeff specifically outlines hindsight experience replay here as a pillar one meta learning architecture. As children, we all learn we tried this, it either worked or it didn't. And it feels like that could be a useful incorporated element in the development of general intelligence as well.
Yeah. So you're referring to the hindsight experience replay, just the ability to, I think right now that's largely useful in the context of avoiding catastrophic forgetting. Being able to replay experience allows for continuous learning on non-IID data sets, which, I mean, right now that's kind of a hack to avoid continuous learning. I think Jeff Clune, it's a hack to avoid catastrophic forgetting, right, and to enable continuous learning, this continuous replay. And I think Jeff Clune has some maybe better ideas on how to allow for continuous learning, which in some of his other papers he explores in more depth, such as his animal algorithm and learning to continually learn. Some other papers where he explores these neuromodulated learning, so neuromodulated learning algorithms where only subsets of the neurons are actually updated with any backprop. And I think if we implement some of those ideas, then we might need less hindsight experience replay, although some of it's probably a good idea as well. So I think that's a valuable thing. We probably want to do some kind of some kind of compressed memory replay. I think DeepMind just had a blog post on that as well. It's the, let's see here. I don't have it up right now, but I think that allows for, a new model and data set for long range memory. I think in here they suggest that long range memory, and they actually specifically refer to the differentiable neural computer with discrete memory, and they point out some of the deficits with those mechanisms and the need to compress representations and memories for experience replay, for the ability to relearn from experiences, but not having to store them all in their uncompressed form, which I think is a very valuable idea.
It feels like attentional mechanisms and curricular learning also factor into this catastrophic forgetting problem space as well.
Yeah, I mean, I think the key idea of catastrophic forgetting is that we can't allow all of the parameters to try to be used to minimize the loss function. We have to have more modular systems, which is what we see in the brain with these cortical columns. And so I think the key idea is that we don't want the write heads to be writing to the whole network at one time.
I don't believe Jeff actually used the term capsule network here, but that's an interesting architecture to talk further about potential implementational concepts for this.
Yeah, I think Hinton he has some good ideas with the capsule networks. And it's exciting to me to see both the manual and the GA side progress. I think that they should both be done in parallel. And we're seeing, I think Jeff Clune says the same thing, that there's value in this manual approach of building, capsules is something he mentions here. There's value in building each individual piece of this, which is why Papers with Code is such a fun website to explore, because they're tracking like 2,600 benchmarks or so. Maybe it's more than that. It's 30, is it 36? Yeah, 30, almost 3,700 benchmarks now on Papers with Code, which is exciting because each individual type of intelligence in its narrow form is being benchmarked, and we're seeing that improvement. And then potentially these different intelligences could be combined at some point in the future, in theory, as some ensemble, right? But it's not clear how that would happen. You could concatenate all of these in some way or to some kind of ensemble. And there probably is some value in that, right? Having these individual types of intelligence narrowly trained and then combined. And I think that's the hacky approach to building AI, which is you just build it one module at a time and then you try to fit them all together somehow. But it's not clear if that approach will work or if it will scale to human level intelligence, which is definitely nowhere close to the global optima of intelligence. So I think
there's certainly value in the development
yeah,
of each system.
yeah,
And I love how Jeff anchors this paper on the idea that it's inherently scientifically interesting to explore this particular domain. Therefore, we should do it. And I think each one of those are inherently scientifically interesting, as is the potential to unify all into a self-learning, self-reinforcing, adaptive, generally intelligent whole.
yeah, yeah. I wish we had more of the research community focused on, Jeff Clune's more exploratory idea of generating the whole intelligence from a single algorithm. Um, but at the same time, it's really cool that we have so much progress on like 3,600 benchmarks, and I think that, in a sense, is this go explore mechanism of exploring how many benchmarks we can create and see progress on. So, I mean, in a sense, that's one manifestation of exploration is the number of different data sets and benchmarks that we see being tracked now. Um, and yeah, but we have so much of the community just focused on deep learning, and it's really refreshing to see the progress being made with evolutionary algorithms and population-based search mechanisms.
There's another section I'd love to incorporate from Jeff's paper directly. This is on page 9. It's unlikely that we will ever know how to directly program a generally intelligent agent. Instead, we will almost certainly have to train a large learning agent on the right training data and/or in the right set of training environments. That raises the question as to what the correct training environments are. Even if we knew what the right set of training environments were, we likely would not get away with sampling from them randomly for training. That would be too inefficient if it worked at all. Instead, we also have to know the right order in which to present the tasks, which may itself be a function of the current learning capabilities of the learning agent. Just as human educational systems have developed curricula for how to teach human learners a variety of subjects, we likely will need to produce effective curricula in order to produce generally intelligent artificial learning agents.
Yeah, absolutely. And this is something that I like thinking about a lot from a human perspective as well, is the curricula that it takes, because I have kids and trying to teach them these, erudite or recondite or complex, abstruse concepts is difficult. And you have to go through this process of building the foundation so that they can learn it one piece at a time. And so, like, it is interesting, the idea of learning a curriculum, learning an optimal path. I think it would be really cool to actually apply that to learning curriculum for humans that's optimal rather than the curriculum that we've all been given. And I think that's fascinating. And it, yeah.
This paper also discusses environmental hyperparameters. Could we think of a potential representation of a hyperparameter as the optimal curricular path for exploring different subjects in different domains?
I mean, I think there's an endless number of types of hyperparameters that you can imagine playing with in any environment. And maybe one aspect of intelligence is how quickly your agents can adapt to changes in the hyperparameters of the environment, or to environmental changes. I think that's one measure of intelligence, is the speed of adaptation to changes in distribution. And Yoshia Bengio is doing some interesting work on measuring that's somewhat related to causal inference. Causal inference appears to be a major factor in how quickly your algorithms can adapt to changes in distribution. With causal inference, they adapt much faster. Without causal inference, they're confused, and they do adapt, but they adapt much slower. So yeah, I think causal inference is something that's uniquely learnable through the approach that Jeff is taking here to a generative algorithm. I think that would tend to develop causal models. Although in humans, our causal inference is pretty bad. Like we often conflate causality and correlation much more than we should. So it's not clear that you would get great causal inference, but even flawed causal inference might give you some really important advantages.
I love this idea that multi-agent self-play is a potential opportunity for us humans to learn new, more positive, generative ways of interacting with each other at large scales, whether we're talking about macroeconomics or even the ideal organization of society, by observing the different game theoretic dynamics that emerge inside of the machine world self-play.
Yeah, and I think that self-play is obviously a big part of what's led to the evolution that we see here on Earth, right? So a lot of the attributes that we see in agents just are clearly shaped by the self-play dynamic of populations, and would not have emerged with one agent, but you have learned. And so it's interesting to think about how much the population-based search mechanisms will differ from what's the norm in machine learning today, is to search for a single model, a single vectorized distributed representation that minimizes some loss function, but it's not clear that that's optimal, or that could even work. We don't have any existence proof for AI other than population-based search mechanisms. Anyhow, I mean, in general, I'm just super excited about the direction that Jeff Clune is going with his research. In basically all of his research, he's exploring areas of AI that are underexplored by the broader machine learning community. And I want to see more researchers, focused on these approaches. I mean, it's great that Jeff's doing it, but he's kind of a maverick in his current research direction, and we definitely, these are valuable areas that need to be explored more. And I think that it's exciting to imagine where we're going to be in AI in 5 years, but I think this is going to be a big part of it. So especially as compute continues to increase, these approaches of evolving a population and evolving the environment, these become more and more feasible. These are more computationally expensive, especially when you introduce evolutionary search rather than gradient descent. These become a lot more costly computationally. It seems
well, the first time around, the evolutionary search algorithm that developed our first instance of general intelligence involved a planet-sized computer. So
right.
Hopefully we can beat that the second time around.
Hopefully, right? And we're definitely making great strides. I mean, it's just incredible to realize the progress that we've achieved in the last decade in machine learning. Just 1 decade, which is such a short period of time if you zoom out to any planetary scale time frame, right? 1 decade, we've seen, a decade ago, nobody was using deep networks for anything commercially, and now you can't imagine building a software company without machine learning somewhere. And I really like the way that this opens the door for open-ended algorithms, right? That especially with evolving the environment, right? You don't know what you're going to end up with. And I think that's exciting. I think it might be interesting to try to evolve the environment from a very primitive environment to something similar to Earth. So having some kind of a direction in the evolution of the environment, but still somewhat of a stochastic process for evolving it. And you have, and so maybe we need to think about minimizing some loss. Well, maybe we need to really focus on how we evolve the environment from its most basic form to something that is the same as Earth. So at the end of the day, these agents end up being ready to introduce into the real world. And at the end of the day, they are learning in an environment that's very similar to what we have today, but they start out with something much less complex.
So much of the work I've done on procedural world generation boiled down to what I could conceptually envision as the ultimate compression algorithm. This idea that given an integer seed and a small number of input floats or vectors describing characteristics of the environment, whether it's aspects of the terrain topology, rainfall in my ecosystem simulations, the types of vegetation that would be a function of those environmental conditions, etc., that would be so conducive to this idea of a world of increasing complexity incorporated as part of the curricular learning for a general intelligence.
Yeah. Yeah.
Jeff
I want
also
to play with your synth algorithm one of these days. So let's,
done. This is happening. Jeff also had this beautiful quote that ties naturally into this part of the conversation. This is from page 18. AI GAs are a bet on learning in simulated worlds. The hypothesis is that we could create general AI entirely in such virtual worlds, although they may have to be complex worlds. However, once general AI is produced, that AI would be a sample-efficient learner that could efficiently learn in our world. For example, such an agent could be transferred to a robot that could learn to maneuver in our world, including helping and otherwise interacting with humans. Thus, rather than specifically designing techniques to transfer from simulation to reality, the approach would not require such adaptation because the general AI would perform that efficiently itself.
yeah, and I think that gets to the heart of the definition of intelligence as sample efficient learners. And there's another paper on the measure of intelligence that recently explored that definition of intelligence and proposed a dataset challenge, the ARC challenge. There was a Kaggle competition for that recently that was fascinating to watch. It ended up being solved with a lot of domain-specific knowledge, but I agree with the hypothesis that a virtual world environment could potentially be the right context in which to evolve sample efficient learners, because that environment is evolving, forcing the agents to adapt quickly to changes in distribution, which I think is what sample efficient learning is all about. One shot, zero shot learning is about being able to quickly adapt to those changes in distribution. And that requires causal inference. And causal inference is something that you learn, I think, through these virtual world environments where you're an agent in a complex world. So, yeah.
Absolutely. Well, anything else we want to cover here that really spoke to you from the paper, Zach?
Oh, it's a great paper. I recommend everyone read it, and also go look at the other papers by Jeff Clune. He has a lot of papers, and you can search for Clune on Archive or on Archive Sanity, and you can bring up. I'm showing 43 papers right now with his name on it on Archive, which is they're all worth reading and fantastic direction to explore. So go explore.
Absolutely. And that's Clune as in Clune.
Yes. And hopefully we'll invite him to join us at some point and bring him on and ask him a bunch of questions. I actually had a list of questions for him once we get him on the show. I think that'd be fun to explore his thoughts on a lot of other areas of AI. I'd love to probe his mind on those things. So brilliant researcher and a brilliant direction that is underexplored, and really encourage anyone in the machine learning research community to maybe part from the crowd and explore these alternative directions, because I think they're promising.
Absolutely. Well, thanks everyone for joining Zach and I today in a discussion on Jeff Clune's paper on AI generating algorithms. Be sure to like, follow, and subscribe wherever you get your pods.